Okay, so till now we discussed about how to perform these linear transformations. Now this brings up a very important idea here that is called as linear independence. So let's talk about what is all this. Linear independence. Now, what is this basically? Let's consider a matrix. To understand this part, let's consider a matrix. So I have, let's say, some data 1 2 3, 3 2 1, 1 1 1, right? Now if you observe the first two columns of this matrix closely, add them together, you will get actually your fourth column. Okay, means you will get the column which will have 4, means 1 plus 3 is 4, so you can say 4 into 1, means if you want me to prove it, you can say column 1 plus column 2 is equal to 4 multiplied by column of 3, right? You can go and verify this statement. Now here basically what is happening, we are able to create another column with the help of these two columns. Means I could have actually constructed my matrix with only these two columns. I don't require the third column basically here. So this, if this sort of things happens, whenever you will be able to express a linear combination of some other particular columns, this is called as linear dependence. Okay, this is called as linear dependence. You can say that linearly dependent column in this case. Now if that is not the case, if let's say my equation was something else, let's say here I would have, let's say, a 3, here I would have, let's say, 17, then there is no way you can represent the same equation in some other format. Then in that case I would have said that it would have been linearly independent equation. Okay, this is basically a linearly independent. Within few minutes you will get an insight that why this is really important from the machine learning point of view. As you might be noticing, what I'm doing is everything in algebra or these things what we are learning, I'm trying to create a connection from machine learning so that it will be more easy for you to relate that why you are learning this, and when you will go to that machine learning topic, you would appreciate that okay, whatever you learn is now making sense to you. Okay, so that's what we will go with that. Now this brings a very interesting another concept. This is basically called as rank of a matrix. Now what is a rank of a matrix? Now a rank of a matrix basically means this is related to your linear dependent columns. Okay, this basically is completely is related to the dependency, linearly dependency of your matrix. So if you want to know specifically, it is the count of the number of linearly independent columns present in a matrix. Now, like in the last example, when I had not changed my matrix earlier and it was 1 1 1, in that case I had two independent column and one dependent column, right? So basically this is going to be my rank. So rank is going to be 2 in this particular example. Okay, so this is basically what you mean by rank. Now that means what? If I have a matrix of, let's say, 3 cross 3, now if my rank is coming as 2, that means we do have a column which is creating a dependency. And from the machine learning point of view, this is very critical for us while doing the data analysis itself, that we have to deal with this. So we may want to remove some sort of basically dependent columns, because those things we don't want to keep up in this case. Now one more thing, like now the question will naturally come in your mind, how I can identify that. Is it easy for me to do that? Yes, using the basically the Python part itself, you can even get the rank. And since you know your dimension of a matrix, you can very easily identify whether you have some dependent column or not. So that's a very nice way to do that. But for doing this, you need to import a package. So you need to say from numpy import lin algebra as LA. So I need to import this package, and let's say I do have a matrix here, np.matrix, and what I'm doing in this matrix is I'm gonna put in some values to it. Let's say 1 3 1, then I do have some more data points, let's say 2 2 1, then let me put one more data point, 3 5 3. Now this is, let's say, my matrix. So definitely ideally you would want the rank to be 3, right? If basically there is no dependency. We definitely want on this side of the matrix all the points to be, let's say, linearly independent. Now if you look at the shape of it, definitely this is 3 cross 3 matrix as we have already seen it. But if you want to get the rank of it, you can always say LA dot matrix underscore rank, and in this I will just pass the value of my matrix S, and you can see that this comes out to be 3. So that means that all my 3 columns which I have is gonna be completely independent, and with the help of any linear combination you cannot create any third column also. So that is basically what this tells us. If you want, you can just play with the same example which I showed you earlier in my notebook, and I was showing you that it was having the rank of 2. You can see that this is exactly going to return you basically the value 2. Now when we are doing all this, this brings up to a concept of something called as multi-collinearity. Okay, so this is basically an important concept. Now this is a very important property to understand when you are talking about linear independence. Now while working with your data, if some of your column vector is linear combination of other, then that variable is adding no extra information to your data matrix. So if there is a linear dependence, then that means there is an extra column. This is not adding any extra information. In the context of a matrix, the term linear independent is typically used in the sense of its column as vector. Now, linear dependence in a matrix is often referred to as perfect multicollinearity. So if you have linear dependence being coming up, that means your rank is coming lesser than your dimension of your matrix, then that means you do have multicollinearity present in your data. And this is in essence a measure of whether there is any redundant information. Means, because as I said, if you have linear dependency, that means that you don't there is an extra column which is not adding any meaningful information. So that means you are adding redundant information in your data, right? So which only going to add unnecessary variance in your data, right? Now basically this is something which we always want to avoid. In fact, this is one of the very common problem while performing data analysis. So before you will apply any of the machine learning algorithm, and when you get the data, you need to do some sort of analysis on that data, which we are going to learn how to do all of that. But while doing that data analysis, we need to definitely figure out that it should be completely linearly independent. If that is not the case, then you may end up with lot of meaningless results. So you have to keep this in mind while solving it. Now imagine when you have 3 cross 3 matrix, maybe you will be able to come up on your own by looking at the data, maybe that this is linear dependent or not. But imagine if you have hundreds and thousands of variables, which do happens a lot in machine learning, then it is going to impact your model, in fact, very badly. You will notice that your model accuracy and everything, whatever is coming up, is completely vague. It is not going to work most likely. So again, it will impact your model, and that's the reason we have to always ensure that we gonna remove all that linear dependence before we start applying any machine learning algorithm. Okay, so this, I hope you now are clear about these points, that what is linear independence, what is the importance of it, and how you can determine in a matrix whether there is a dependency problem or not. Now another concept which is very important in your matrix is called as determinants. Okay, determinants. Now when I say determinants, this is an idea related to square matrix which happens only on numerical data. Now basically one very important thing would be that in a matrix, basically when you have a data sets, you don't want your determinant value to be 0. Okay, I will tell you why. It have an impact when you will go to inverse of a matrix and so. Now let's understand basically what we basically mean by this determinant. Now if I intuitively want to understand this determinant in a 2D space, basically this is the area that one square unit is expended or shrunk to when your linear transformation is expressed by that matrix on a TD space. If you want to understand it, you can basically take up this example. This will make more sense to you. Let's say I have this example of ABCD, and if I want to determine the determinant of it, it means that AB, okay, basically A multiplied basically AD, sorry, I have done a typo here. So this is supposed to be AD, means these two values need to be multiplied, then minus these two values to be multiplied, so BC. So this is what defines your determinant value. Now you may ask me a question, what about if this matrix was of this form, 3D matrix, A, B, C, D, E, F, G, H, I. Now what you would say about it? Now in that case, again it's quite simple. What we do in this case, if I have to determine the value of determinant for this matrix B, I would take it like A into, now do the determinant of these two part. Okay, so we will say determinant of basically EF and HI. Okay, this is basically the first part. Then the second value we take it minus, so plus minus plus minus plus, yeah, this is the logic we go with. So then after that we will say minus B. Now when we say B, we will take the determinant of DGFI like this. Okay, so basically again we're gonna put here as DGFI. Okay, now after that we have to say again plus C, now into, now below C leave it, and after that whatever value just take it up. So that means we have to take DEGH. So the same thing you can expand it now to for n dimensional data if you want to, the way we were doing it till now, even for linear algebra portions, right? So same way you can expand the same idea to very easily to n dimensional data set. Now let's understand another concept which is coming up from your again from your determinants, is inverse of a matrix. So now we're going to understand that how to determine inverse of a matrix and what's the significance of this. So whatever we were learning till now, determinants and all, how this is going to be really important. Now if you want to basically understand this particular point, basically if it has a very interesting property. Okay, so the important property is that if I say A cross A inverse, basically this is called inverse of matrix, this is going to return me identity. Okay, so somehow if I have a matrix A, and if I can somehow find another matrix with, if I multiply these two matrices, that matrix should return me the identity matrix. So if that is possible, that means that this matrix using which we were able to get this identity matrix is called as inverse. Now how this is going to be useful and how to calculate that, so let's first focus on how to calculate that. Now here let's say I have a data set like A, C, B, D, and I have to calculate, let's say, the inverse of this matrix. So first I have to take the determinant of these two values, which is going to be AD minus BC, and then what I do, I exchange A and D, so I will say DA, and these values I just have to put negative to it, BC, right? So this is how you can find the inverse of a particular matrix. Now how this is going to be useful, let's say I have some sort of matrix A. Okay, let's say I have this sort of matrix A, and X is an input vector, and let's say I have a value B to it. So you can think of A like a matrix, right? So this is a matrix, and this is, let's say, x1, x2, and so on, right? And this is in front of value B. So now if I want to get the value of x1, x2, x3, or whatever we have, we can easily do it with the help of these inverses. So we can say X is equal to A inverse B, and if it is going to return me the output, this is going to basically be, this inverse is going to be very helpful in getting me the value of X basically here. Okay, so this is a very interesting thing about it. In fact, if I will tell you a few more very interesting properties if your matrix is going to be inverse. In fact, not all matrices are going to be inverse, because if your diagonal element have any value as 0, then it will not work, or if your determinant is 0, then again it is not going to give you any sort of inverse in that case. So basically let's talk about some of the interesting property here. So the inverse of a matrix will only exist if all of your columns are linearly independent. That is one very interesting property here. If in your matrix you have a linear dependence coming up, then in that case, definitely that linear independence will not let you create any inverse for it. Similarly, if you have a matrix and you can get the inverse only and only if there is no element in the diagonal which is 0. So that also another important property. Now, if two matrices A and B are both invertible, if you can basically get the inverse of it, there's a very nice property about it. If I do calculate the inverse of this two multiplication, this is equivalent to saying B inverse into A inverse. Okay, so again you can apply the same logic even for more matrix as well. So like if you are doing this, then you can also say D inverse into C inverse into P inverse into A inverse. Okay, so like this also you can define or expand this particular property. Now, as I said, your determinant should not go 0 if you really want to basically define your inverses, okay, because this is very much related to that. So this concludes this particular topic, and you can see that this was one of the very important topic from machine learning point of view as well.